this lecture, we will consider an application of what we have just learned to some specific problem of overbearing reflection. And the classical textbook problem, which you may find in, say, a third volume of the course of Landau and Lifshitz, is scattering of the reverted harmonic oscillator potential. So this is u of x as function of x, and let us say that u of x is minus u naught x squared, and this problem is about reflection of a particle at certain energy E, which lies above the peak of the barrier. And of course, as we understand on general grounds, that particle which is incident, say, from the left, will transfer almost completely if energy is large enough, and will scatter back with some small probability. So this is actually an archetypical problem. It can be applied not only for potential which is x squared everywhere, but also for scattering from the potential in the vicinity of its top, as long as it's quadratic at its top. So for example, we can imagine that we have some potential of the following shape, and as long as energy is not too far from the peak of the potential, the formula which we will now derive actually applies equally well to that kind of potential. So it doesn't have to be quadratic everywhere, but the case of potential quadratic everywhere is just simple to solve. So at the first level of understanding, let us try to apply quasi-classical approximation for analysis of this problem. And in quasi-classical approximation, we know that there are two solutions to the Schrödinger equation. And these two solutions correspond to particle moving to the right and to the left. And of course, a full solution of the Schrödinger equation has these waves only as asymptotic states. And in principle, we know that equation, say, the Schrödinger equation has the following function, say, which corresponds to the particle transferring to the right at x going to plus infinity, has this function as an approximate solution. So let us choose a sign plus here instead of both of them. So it is just p dx prime. So this kind of quasi-classical wave function with only one wave does almost solves the Schrödinger equation. But of course, this is not what we need, because this kind of solution corresponds to the absence of the complete absence of the reflected wave. And we do understand that there should exist some, although small, probability of scattering back. And evaluation of this probability is precisely the topic of this current lecture. Нет, еще нет, но я вот немножко, у меня тут застряла хрень. Сейчас я продолжу через секунду. So let us now try to understand how exactly the quasi-classical approximation is going to break down, why, and how to take this breakdown into account. So consider, as we have just discussed in the introduction, consider complex plane of x. And we know that although there are no points where quasi-classic breaks down on the real axis, because for real x, momenta for this scattering geometry is always non-vanishing, is determined by the following standard expression, and it doesn't vanish anywhere on the real axis. So very naively, quasi-classics is going to work everywhere, and there should be only one wave. But in fact, we know that something is not complete in this description, and this something is of course related to the fact that in the complex plane of the coordinate there are certain points where quasi-classics does not actually work. And as long as these points are not too far from the real axis, they do contribute to the real scattering process. So these special points, we need to consider only one of them. Let us call it x star, and it is found from the condition p equal to 0. That is x star equals to I square root of epsilon over u naught. So this is exactly the point where quasi-classical momenta vanishes. And in principle, although it doesn't lie on the real axis, it does have some influence on what is happening on the real axis of x. And let us So this is something which prevents us from using quasi-classics, and let us take into account the existence of such a point explicitly. And the key idea of this of our treatment will be that in the vicinity of this special point, the Schrödinger equation will simplify a lot, as we will see momentarily. And we make use of this simplification to match the quasi-classical solutions, say in this region, corresponding to the scattered, to the transferred wave, and quasi-classical solution in that region, corresponding to incoming and reflected wave. So, and matching these quasi-classical solutions with the solution in the vicinity of the stopping point, turning point, we will find the reflection amplitude with certain reasonable accuracy. So let us see how this works. So in order to understand it, let us consider, let's write down explicitly a Schrödinger equation. So this is the Schrödinger equation for that kind of problem, the most general form. And let us now expand, let us now try to simplify this equation in the vicinity of the turning point. So let us introduce new variable and write x equal to x star plus something which will be considered small. This x star is exactly this turning point plus alpha z. And this z will be our new variable for the Schrödinger equation. And alpha is some parameter which is free for now, and we will choose it in order to simplify the equation as much as possible. So first step will be to substitute this change of the variables into the Schrödinger equation. And then we will throw away terms which are quadratic in z, assuming them to be small, in a sense that, say, consider, for example, x squared. It has several contributions. It has x star squared plus 2 alpha z x star plus alpha squared z squared. We will assume the small enough vicinity of the turning point so that quadratic term can be neglected with the in comparison with the linear term. So we will throw this away. So substituting this into the Schrödinger equation, we come to the following result, so intermediate result. Now we differentiate with respect to new variable z. So what we have here, this is u naught x squared psi. So this is u naught psi, and then this x squared has several contributions. First of them just simply cancels the energy. This term, if put in the Schrödinger equation, just cancels the right hand side, and the quadratic term can be neglected. And all we are left with is 2 alpha z x star. So this is equals to 0. So before proceeding, let us substitute here explicit expression for x star. So actually, and multiply everything by 2 alpha squared. So as a result, the equation becomes psi double prime plus 4 alpha cubed z u naught times I square root of epsilon over u naught equal to 0. So, so everything apart from z here is just a number, a complex number though. So anyway, this equation is already quite familiar to us, and we spend a lot of time analyzing the properties of this solution. And of course, this is nothing but area equation. Almost an area equation because in its canonical form, it has the following shape. And it has well-studied solutions. In order to reduce our Schrödinger equation in the vicinity of the turning point to the canonical form, we can adjust our parameter, which is free by now, which is alpha. And in particular, we have to require that for alpha cubed I square root of epsilon u naught equals to -1. So with this in mind, we notice that Сейчас, одну секунду, паузу, сейчас знак проверю. По-моему, тут был плюс раньше. Что-то я где-то перепутал знак. А, нет, все правильно, все правильно. So this equation can actually be rewritten in a explicit form, and in an explicit form, it actually tells us that alpha equals to 1/4 square root of epsilon u naught to the 1/3 and I to 1/3 power. And of course, this expression is to a certain extent formal because there are at least three square roots of I. And we need to choose alpha. With arbitrary choice of alpha, we will reduce our equation to the area equation, but we'll use this freedom to simplify our life slightly. So with this in mind, please note that this is just purely a real positive number, and we need to choose a proper square root of I. How do we do it? In order to make a proper choice, let us briefly recall the properties of the certain solutions of this equation.